Welcome, my dear students, this new session. In this session, we discuss some examples and exercises on linear transformations. In the last class, we discussed about the theorem, which we say that if we have a basis, we have a map T from V to W, and V1, V2, Vn be the basis of a vector space V, and W1, W2, Wn be any vectors in W. There exists a linear transformation which map is a unique representation of a T of Ui is equal to Wi. We have to prove this theorem. Okay, in this class we have to base on this theorem. We just try to solve different types of examples and some exercises for this thing. Okay, let's begin with this question. We have a define a linear transformation T from R4 to R3 in terms of the standard basis. We have this is given, and T of E1 is giving this form, all this T of E2, this T of E3, and T of E4 is this. Now question is this: find the linear transformation of a T. So by the previous theorem, we can say that clearly T of V I is equal to, you have a Wi. So there is a, means this is the basis is giving. So we have to take any bit R4. So we have to take some x1, x2, x3, x4. These are the vectors for R4. If these are the vectors of R4, then this B is a basis for this vector space R4. So that means this is a basis, means this vectors can be finite linear combination of these elements of this basis. So this can be written as the form of we have to write x1, x2, x3, x4 can be written as alpha times of E1 plus beta times and so on. But because these are the E1, E2, En, this you know that E1 is the form of you have a 1, 0, 0, 0. E2 is the form of a 0, 1, 0, 0. E3 is the form of a 0, 0, 0, 1. And similarly, E4 is the form of a 0, 0, 0. We have a 0, 1. Sorry, this is equal to 1. Okay, so now this means this can be written in the form of x times of a x1 is equal to E1 plus x2 is equal, after simplification we write into this form, x3 is equal to E3 plus x4 E4, and now we have to calculate the linear T of this x1, x2, x3, x4, and T of we have a x1 E1 plus x2 E2 plus x3 E3 plus we have to just say that we have a x4 E4, and now by the linear T of a T we have to just say that x1 T of E1, x2 T of E2, x3 T of E3, x4 T of E4. Okay, so this can be written as x1, then E1 is equal to T of E1 we define in the form of a 2, 1, 3 plus x2 is defined in the form of a minus 1, 0 and 1 plus we have a x3, and this defined in the form of a 0, 1, 5 of plus x4 defined as a minus 5, minus 2 and minus 5, and this can be written in the form of this form. We can write x1, 2x1, and then you have a twice x1 minus you have a x2, x3 is 0, and then minus 5 x4, and now we have a x1, now we have a x2 0, then we have a plus x3 plus we have a minus twice x4, now we have again is x1, and then we sorry, this is nothing, this is we have a 3x1 plus you have a x2 plus 5x3 minus 5x4. So this is the general transformation of this T of x1, x2, x3, x4 in the form of this can be written in this form. Now you can verify this clearly if you take a E1, if you have a T of E1, the T of E1 means you have a 1, 0, 0, 0. If you substitute here in this form, we have a clearly you just take a this is 2 when here you have to do 1 0 0, so this is equal to you have a 2 x3, here you have a 1 and then you have a is equal to 3. Similarly other terms you have to calculating, this is verify. If you take a t of e2 means you have a 0 1 0 as 0 is nothing but is equal to we have a this is equal to you have a minus 1 from here, this is equal to you have a 0 here, then you have a 1 is here, then satisfy these two conditions. So this means this is the general representation of a linear transformation. T of x1, x2, x3, x4 can be represented in the form of a in this form. Okay, so now we can check by this. So this another problem we have to take a different. We have to just giving the R3 be a linear operator such that T of V1 is equal to this, T of 1 0 0, T of 0 and 3 is equal to 0, and clearly you can see these vectors we have a vectors is equal to we have a 1 0 0 and then we have a giving 0 1 0 and then we have a giving 0 0 1, and this is clearly these are the bases for R3. Why? Because these all three vectors are linearly independent, they are the standard basis. Again he says find the value for t of minus 3, 2 and 4. So if we have a vectors is this, so we can write minus 3 to 4 as a linear combination of a minus, because this is the standard basis. We can write this is equal to 0 1 0 plus we have a 4 times 0 0 1. So this is a because of this basis, this can be representation into this form. This can be written as a linear combination of the element of the basis. So we can say that t of minus 3 to 4 is the form of a t of minus 3 1 0 0 plus 2 times of a 0 1 0 plus 4 times of a 0 0 1, and t is a linear. So this is minus 3 t times of a 1 0 0 plus 2 times of a we have a t of 0 1 0 and plus 4 times of a t of 0 0 1, and this is equal to minus 3 times t of 1 0 0 is equal to minus 2 1 0 plus 2 times you have a 3 minus 2 and 1 and plus 4 times you have a 0 minus 1 and 3. This can be written as a minus ka 6 minus ka 3 0 and plus you have a 6 minus 4 and 2 plus you have a 0 minus 4 4 3 is a 12, and then now you have a minus 6 plus 0 and minus 3 minus 4 minus 4, then you have a 0 plus 2 plus 12, and then this can be written as a minus 6 is cancelled out, so you have a 0 and then you have a minus 11 and then you have a plus ka 14 is this. So value of this is can be written in the form of this. You have a 0 minus 11 and 14. So this means this, and this is another question is saying that you have to find the t of x y z for all x y z belong to z R3. Okay, so this first one I already solved into this form. We just say that we have a like this. So we have a okay, this is plus 6, so plus 6, okay, 12. So it is a 12, 11 and 14, and now we have to try to like this. So this means I just say that we have to take a x, y, z is the element of a R3. So x, y, z can be written as a linear combination of the elements of the basis. So 1 0 0 plus y of 0 1 0 plus z of 0 0 1, and now operate t, and so we have to operating t into this form using the linear t, the t of x of 1 0 0 plus y of t of 0 1 0 plus z of t of 0 0 1, and now x t of 1 0 t of 1 0 0 you have a value is here, so you have a minus 2 1 0. So this value is equal to, we have to write is equal to minus we have a minus 2 1 0, so minus 2 1 0 plus y times the second term is you have a 3 minus 2 1, so 3 minus 2 1 plus z times you have a 0 minus 1 3, so 0 minus 1 and 3. So this can be written as a minus 2x plus ka 3y, and then you have a written as x minus ka 2y minus ka z, and then you have a y plus you have a 3z. This is the you have a general formula for a t x y z. So this is we can just say that is the general formula of a this we can written to this form. Okay, so from here I just try to find the value for this question is 12 11, so minus 3 2 4. So from here we also calculate from by directly. So if we have to just say minus 3 2 4, so we have a we take a minus 2 sorry minus minus 3 2. So we have to calculating this t of minus 3 to 4. So minus 3 to 4 means we have to write in the form of a minus 2 into minus 3 plus 3 into 2, and then you have a x is equal to you have a minus 3 and minus 2y, then you is equal to minus ka 4, and then you have a minus ka 4, then you have a y is equal to you have a 2 plus 4 3 into 4. So this is nothing but is equal to you have a plus 6 plus 6 or 6 you have a 12, and then you have a minus ka 11, and then you have a less ka 14. So this means by this general formula we can verify that whatever we have to calculating is equal to minus 3 to 4 is giving the same values of a this again. Okay, now we have a next we have some different, we have to solve these two questions with the standard basis. Now I will take a different types of a basis. So I just take a this basis b is equal to 1 1 1 0 1 1 1 1 1 0 or 1 0 0. This is a basis, and t from R3 to R3 is a linear operator because both the vector spaces are the same. So t of 1 1 1 defined into this form, t of 1 1 0 defined into this form, and then t of 1 1 is equal to. Now we have to just find a formula for t of x1 x2 x3, and use this formula we have to calculate the value for 2 4 minus 1. Because this is the basis of R3, so we take any arbitrary vector x1 x2 x3 belongs to the R3. Now if x1 x2 x3 are these are the basis value vector of a R3, so this means this can be written as a linear combination of the elements of this basis. So alpha 1 can be written as alpha 1 1 1 plus alpha 2 and so on. Now by this I just say that I is equal to this. Now we can write into this form. This can be written as a you have a alpha 1 plus alpha 2 plus alpha 3. Now you have a alpha 1 plus alpha 2. Now you have a alpha 1. So this implies that clearly alpha 1 is you have a giving is equal to you have a x3, and alpha 1 plus alpha 2 is giving you a x2. So alpha 2 is giving you a x2 minus x3. Alpha 3 is giving you a x1 minus alpha 1 minus alpha 2. So x1 minus you have a alpha 1 is equal to x3, and then you have a minus x2 or minus minus plus x3, x3 cancel out. So you have x1 minus x2. So alpha 3 is equal to x1 minus x2, alpha 2 is equal to x2 minus x3, alpha 3 is equal to alpha 1 is equal to you have a x3. So after simplifying we have to just take, after this we have to getting into a this equation. So thus this can be written x1 x2 x3 be written in the form of a. So on solving the above system we get clearly into this form. So thus we substitute the value for alpha 1 alpha 2 alpha 3 into this equation. So x1 x2 x3 can be written as x1 x3 of this x2 minus x. Now we have to operate t from here. So t of x1 x2 x3 can be written as a by this form, and t is a linear, then can be written as a x3 t of 1 1 1 plus x2 minus x3 t of 1 1 0 plus x1 minus x2 t of 1 0 0 in this form. we write into this form. Now substitute the value for t of E1 1 t of 1 1 0, t of 1 0 0, and then this can be written substitute x1 x3 in times this plus x2 and so on. This can be written in the form of there is a no term x1, we have a, so this can be written as a x3 plus x1 minus x2, and then we have a twice times of a x3, and then we have a plus 3 times of a x2 minus 3 times of x3, and plus 5 times of x1 minus 5 times of x2, and then last one you have a 4 times of a x3 and plus 2 times of x2 minus 2 times of x3, and plus we have to multiply the minus, so this means is equal to minus ka x1 plus ka x2, and this if we have this is the simply the x1 minus x2 plus x3, and now you have a x this is x2, so 3x2, and then you have a minus 5x2, this is 5x1, so you have a 5x1 minus 5x2 and then plus 3x2, so you equal to minus ka twice x2, and then you have a minus 3x3 and 3x3, so you have a minus ka x3, and now you have a, again you have a minus ka x1, now 2x2, and this is equal to plus ka 3x2, and then 4, and then is equal to minus, this is equal to minus ka twice x3. So this means this general formula can be written to a this form. We have to just say that into a this form we have to write in this form. Okay, so now now we have to write the next part is we have to calculate the 2 4 and 1. T of 2 4 1 we have to substitute the x1 is equal to 2, x2 is equal to we have a 4, x3 is equal to minus 1 in the all of them, and then we getting this is equal to form of the form of this form minus 1 3 and 8. This is clearly we have to say that the t of 2 4 minus 1 can be written into this form. Okay, next problem we have to take some matrix form. We define a map linear transformation from polynomial of all the degree less than equal to 2 to 2 by 2 any 2 by 2 matrices, and we define a this now first we have a elements are giving, suppose we have to take this 1 plus x, x plus x square, and then 1 plus x cube, sorry 1 plus x square, so this is 1 plus x square. Now clearly we can verify these three vectors are linearly independent. How we can just say that? We can say that alpha times 1 plus x plus beta times x plus x square plus gamma times you have a 1 plus x square is equal to 0 vector. So you have a alpha plus gamma is equal to 0, then you have alpha plus beta is equal to 0, then you have a beta plus gamma is equal to 0. By these two we can say that alpha minus alpha minus gamma, so alpha minus gamma is equal to 0, and then by these two we can say that alpha is equal to 0 and alpha is equal to 0, then gamma is equal to 0 and beta is equal to 0. So these three vectors are clearly linear independent, so this form a basis. So this is clearly is a form a basis of this vector. So this if these are the bases, that means we take any polynomials of a degree 2, so a0 plus a1x plus a2x square belongs to the we have a p2, and then this is a0 plus a1x plus a2x square can be written as a finite linear combination of the elements of this. So we have alpha times 1 plus x plus beta times 1 say we have a x plus x square, or plus gamma times you have a 1 plus x square. Okay, so now we have to simplify these system of equations for alpha, beta, gamma, and then substitute here and then operate the t, and then we get the required result. So this means this is equal to, so this means this giving you have a alpha plus gamma is equal to you have a naught, you have alpha plus you have a beta is equal to you have a a1, you have a alpha, sorry this is equal to you have a beta plus gamma is equal to you have a this is a naught a1 a2, so this is equal to a2. Now again by these two we can say that alpha minus gamma is equal to a1 minus a2, and then we have a given alpha plus gamma is equal to, we have a naught, we have to adding these two, we getting twice alpha is equal to a naught plus a1 minus a2. So we have alpha is equal to 1 by 2 a naught plus a1 minus a2. Now substitute the value for anywhere is this alpha. So beta is equal to, you have a1 minus alpha, this is equal to a1 minus 1 by 2 a naught plus a1 plus minus a2, and this is nothing but is equal to, so you have a a1, so you have a clearly a1 minus ka, you have a 1 by 2 is outside, so you have a 2a1 minus a1, and then you have a minus ka a naught and plus ka you have a a2. And now similarly we can say that gamma is equal to, you have a naught minus alpha, so this is equal to a naught minus 1 by 2, alpha is equal to, you have a naught plus a1 minus a2, or this is equal to, you have a naught 1 by 2 times a naught minus ka a1 plus ka a2, and then substitute the values of this to here, we can just say that into this form. So we have to take arbitrary vectors, so just we have to calculating all the values of this, clearly we have to, and I just repeat copying here. So alpha is equal to 1 by 2 a naught plus a1. So alpha is equal to, you have a 1 by 2, we have a naught, we have a naught plus a1 minus a2, and then we have a beta is equal to 1 by 2, and we have a value is equal to, we have a beta a1 minus a1 minus a naught plus a2, and we have a gamma is equal to 1 by 2, and then this value is, we have a naught minus a naught minus a1 plus a2. So we have a t of a naught a1x a2x square can be written in the form of this alpha is equal to 1 by 2 a naught a1 minus a2, and this is the value for 1 plus x. So you have a 1 plus x plus 1 by 2 beta is equal to, you have a a1 minus a naught plus a2, and then you have a value for this is equal to x plus x square, and then plus you have a 1 by 2 a naught a1 plus a2 x plus you have 1 plus x square, we have 1 plus x square. Okay, t we have to operating into this form. So this can be written in the form of a 1 by 2 a naught plus a1 minus a2 t of 1 plus x plus 1 by 2 a1 minus a naught plus a2 t of x plus x square, and plus 1 by 2 a naught minus ka a1 plus ka a2 t of 1 plus x square. So 1 by 2 we can say that a naught a1 minus a2. Now we have a matrix is a 1 0 0 1 0 0 0, and then plus 1 by 2 a1 minus a naught plus a2, and then we have a matrix as you have a we have a matrix 0 1 0 1 1 0, and then we have a plus 1 by 2, and then you have a naught minus a1 plus a2, and then this is a matrix we have a 0 0, so we have a 0 0 0 1, and now we have to substitute into this form. So this is simply into this form. I just take this. So a b c, I take a naught b naught of this, the same thing. We have to calculating into this form, and this means we have to just substitute the value, and then because 1 is not there, so this is first term is equal to this form, then we have a second term is this form, then third term is also this, and then we have a general 1 by 2 of the matrix into this form. So T can be T of Px can be written into a this form. This is complete the form of this thing. Okay, so now determined with whether there exists a linear map in the following cases. Where does exist, give the general formula. Now clearly you can see this 1 2 and 2 1 are linearly independent. So 1 2 and 2 are linear independent, that means there exists some linear maps. So these two form a basis. So we just again we have to just take x and y are the element of a R2, and this x and y can be written in the form of a we just say that is equal to 1 2 alpha times plus beta times of a 2 and 1, and then similarly we can simplify this can be written alpha plus 2 beta and 2 alpha plus beta. So you have a alpha plus twice beta is equal to x, and twice alpha plus beta is equal to y, and then you have to multiply it by this is 2, and then subtracting this like, and then simplify this, then you getting easily solve this. So you can just try, if you want you can just take multiplied by 2 and then take a subtraction. So this is equal to minus ka you have a 3 alpha, and then this is equal beta is cancel out, so you have a x minus ka 2y. So alpha is equal to you have a 2y minus x by 3, and similarly we can just take a beta is equal to nothing is equal to y minus 2 alpha, so is equal to y minus 2 by 3, and then you have a 2y minus x. So you have a take a is equal to 3y minus ka 4y plus ka twice x by 3. So this is equal to twice x minus y by 3. So this means we can say that t of we just say that this is t of x y is can be written in the form of alpha is equal to you have a 2y minus x by 3 1 you have a I directly is equal to 3 0 plus we substitute the value for directly, then you have a 2x minus y by 3, you have a 1 2, and then simplify this, we get the result of a this is a linear transformation, general formula for a linear map. Or similarly this we have to this giving, because this is not a we cannot find this. Why? Because you can we have a R2, and then we have a vectors within the set of a B is equal to you have a 0 1, and you have a clearly you have a another is equal to you have a 3 1, and then you have a 3 2, and now you see clearly 3 2 can be written in the form of a 3 1 into 3 1 plus 1 into 0 1, and this is if t of 3 2 you calculate 3 t of 3 1 plus t of 0 1, and now 3 t of 3 1 is equal to you have a 2 comma 2 plus t of 0 1 is equal to 3 4, and now this is equal to nothing but is equal to 5 and 6, but you have defined t of 3 2 is the form of a 5 of 7, this is not equal to 5 of 6. So this means 5 6, so this implies this is not equal to t of 3 comma 1 plus because it's written in this form, but there are two different values here. So this is clearly we can say that this map is not a linear. Why this is non-linear? Because we have to working in R2, but there is in the basis is a 3 elements, so this is clearly linearly dependent. So there is no guarantee is giving to a such a matrix map is exists is a linear map. Similarly, this polynomials things we have to try. This is clearly this vector, and this vector are linearly independent. So this is clearly form a linear transformations, and this linear transformation we can easily find the general formula of a linear transformation. So you just take a plus bx plus c x square can be written in the form of a alpha times 1 plus x plus beta times 2 plus x plus gamma times x square, and then you can just see this you have a alpha plus twice beta is equal to you have a alpha plus beta is equal to you have a b, and you have a gamma is equal to you have a c, and then if gamma is equal to, you have already c is there, then simplify these two, you have to just subtraction these two, then you have to getting the beta is equal to a minus b, and if beta is equal to a minus b, you have alpha is equal to b minus alpha, b minus beta. Also this implies that b minus a plus b, so this is equal to minus a plus 2b, and substituting this, and then we have to write into this form. We can this can be written in the form of t of a plus bx plus cx square is written in the form of alpha is equal to, you have a minus a plus 2b t of 1 plus x plus beta is equal to, you have a minus b t of 2 plus x plus gamma, gamma is equal to c t of x square, this is equal to, you have a 0 given, and this is nothing but is equal to minus a plus 2b 1 plus x, and plus you have a minus b into x plus 3x square. So this is we can just write in the form of this, they have a this x, so you have a minus ka a plus ka twice b, and then we have to write plus x coefficient is equal to minus a plus 2b plus a minus b, and then you have a x, and plus you have to write is equal to form of a, in the form of a, this is nothing but is equal to a minus 3 times of a minus b x square. So this x is cancel out, so this can be written in the, this is the general formula for a polynomials of a this thing. Okay, so now I just take this last exercise example here. Today lecture, determine non-zero linear transformation R2 to which map all the vectors. Is saying that we have to working into this. This is the line into this form. We have x is equal to y is a line. Is saying that all the vectors lie into x is equal to y onto the origin. So those vectors is mapping into the origin. So this means if we take a span of this set is the can be written generated by, this means x and y, we have all the span a set, we can write it, suppose w can be written in the form of you have a x comma x such that x is the element of R. So span of this w is equal to nothing but is equal to, you have a 1 comma 1, and then we have a given, what is the given, 1 comma 1 is equal to 0 comma 0 is mapped to 0. So we find to write a general transformation. Now by the method of we have extended the basis, we can extend the basis of this. So we can extend the basis of this 1 comma 1 can extend any vector, because third point any vector of this which is a clearly linear independent, and also we define this 1 comma 0 is equal to 0 comma 1 form, any form we have to define general. And now we have a x and y is the element of a R2. So x and y can be written as a alpha times of a 1 comma 1 plus beta times of a 1 comma 0, and this implies that you have a alpha plus beta is equal to x, and alpha is equal to, you have a y. So beta is equal to, you have a x minus y. So we can write in the t of x and y the form of alpha is equal to, you have a y t of 1 comma 1, and then plus beta times of a, you have a beta is equal to x minus y, this is x minus y, and then we have a t of 1 comma 0, and this is 0, so y into 0 0 0 plus you have a x minus y, 1 comma 0 is equal to 0 comma 1, and now this can be written in the form of a 0 comma x minus y. So t of x y, so we can write the general formula of a t of x y is the form of a 0 x minus y. And now you can just check anything is equal to if you take a x1 y1, if you take a 1 1 when the line x is equal to y, this is map is equal to y is equal to 0 0 is map out. So this is the general formula for this. So now I just stop to this lecture here, and not here, I just give you one example for your home assignment. The same problem I just change, in place of x is equal to y onto origin to x plus y is equal to 0 to onto themselves, and this map t should be not be the identity map there. So thank you very much for this lecture. This is for your home assignment. So I stop here today lecture. In the next class I will start with the kernel and range, and then we have to the rank and nullity of a linear transformation. Thank you very much.